Hi, I'm Tom Ralston, Aspen Tech's Product Manager for Heat Exchanger Design and Rating. In this tutorial, we're going to look at the design of an overhead condenser for an atmospheric crude distillation unit. The crude unit in question is modelled in Hysys. Our task is to perform preliminary design on one of a pair of condensers performing the overhead duty. We'll see how to import process and property information from Hysys into Aspen Air-Cooled Exchanger. We'll use air-cooled to do a design optimization and find the geometry of unit we require. This will require us to set some key process requirements and to run the design optimization. We'll then review the results and prepare a model to explore changes in process conditions within Hysys at some future point. Let's open a new case in Aspen Air-Cooled Exchanger. Let's import data from Hysys. This is the case we want to select. Let's look quickly at the Hysys case we have here. And you can see here we've got part of a crude distillation unit with some of the preheat train modelled, the main atmospheric crude heater, the atmospheric distillation column, and here we have the overhead stream going off, and this is the pair of air-cooled condensers that we're focusing on, and we're going to design a unit to handle the duty of AC 101. If we return to Aspen Air-Cooled Exchanger in our case, we want to select AC 101, and we can see the process conditions for the unit. We want to change the intermediate and outlet pressures to have nice round numbers. So I want 1.9 bar for the intermediate pressure and 1.86 bar for the lower bound. So we click OK, and under Use Properties here we want to make sure we cover the full range of pressures, so we have isobars for each of the three pressures we've selected. Click OK again, and our process and property data are updated from Hysys. When designing an air-cooled heat exchanger, it's often difficult to determine how much airflow we require, in addition to determining what the geometry of the unit should be. For that reason, we provide an option called Design with Varying Outside Flow, and this will optimize to find the best airflow for our requirement as well as the air cooler geometry that we need. Let's also go to the process data, and we can review quickly what's been specified from Hysys. We want to set the allowable pressure drop to 0.1 bar. So here you can see that the default was 0.1, but let's explicitly set it. And we'd like to specify the process fouling as 301 in SI units. If I now go to the process conditions for the outside stream, our ambient air temperature for this design is 25 degrees C, and a good practical value for allowable pressure drop on the air side is 150 pascals. Before we run, I'd like to set here in the design options some key process limits. I'd like to make sure that the range of face velocities on the air side of the cooler is between 3 and 4 meters a second. This is a good practical value, I believe. We're now ready to run the design optimization. So let's do that by clicking Run. And here you'll see in the status window that the program will go for different airflow rates. It will first establish, by that means, the optimum airflow rate, and then having done that, it will redesign to make sure we have the best geometry for that optimum airflow rate. This is a complex calculation with a lot of internal iteration, so it may take a couple of minutes to complete. Once it's found the optimum conditions, the design is completed very quickly, and you'll see a message like this in the status window that the program's finished normally. I usually close that window and look very quickly at the performance output. If we look at the process output form, we can see that in the upper section we have the process conditions, including the calculated required airflow of 536 kilograms a second. We also have process temperatures and pressures and so on. Note that the program for information here provides the calculated inlet dew point and in this case the outlet bubble point for the process stream at the local pressures inside the exchanger. The center section has some calculated thermal and hydraulic information. The bottom left we see integrated overall heat transfer duty and the integrated overall coefficient and mean temperature difference, and here we can also see the area ratio for this design. That's the ratio of actual area in the geometry to the required area for this duty. And then on the lower right we can see a summary of the geometry of our unit. So for this duty we require 3 bays with 2 bundles per bay. There are 200 tubes in each bundle, 5 rows in the bundle. The bundle is arranged in a single pass, and we require 2 fans for each bay. There's a summary here also of the tube performance, which was defaulted information. We could change that if we wanted to, but in our case we took the defaults. The graphic that you see at the very bottom of this stream is an illustration of the magnitude of the heat transfer resistances. On the left we have the outside or the airside resistance in this case. The small black bar represents the magnitude of the tube wall and the fin resistance. This red bar represents the magnitude of the process side fouling resistance, and then this second large yellow bar is an indication of the magnitude of the tube side heat transfer resistance. So in this arrangement we can see very quickly that the tube side resistance is dominant, and if we wanted to try to make the design more compact, perhaps something we could do is try and influence that tube side resistance. You may want to look at other aspects of the design that you've produced. For example, you might want to look at the setting plan, and here you see an illustration of the overall arrangement of the unit as it would be. You can see the 3 bays, you can see 2 bundles per bay. If you right click anywhere on this, you have some options about what you view and other options like printing and saving. If we want, we can look at the plan only view, and left clicking anywhere in here, you can left click and drag and zoom into this setting plan. So a lot of useful functionality there. We can also look at the tube layout. Here you can see the 5 rows of our air cooler bundle. The tubes are individually numbered with pass numbers, so here it's very simple. You can see everything's in a single pass. So some useful outputs there. You may want to also look at the API specification sheet, and you can scroll through that. This can be printed if you want it. Some times it's useful to look at the interval analysis, and you can look at some of the plots here, for example pressures or stream temperatures, and so on. So we've completed our design. Let's save the case. So I'm going to save as and designate a file name. If you want to perhaps use this case to embed back into your Hysys simulation, then you'll need to prepare a rating case from this design file. And the way we do that is we go to Run, Update File with Geometry, and that creates a rating case of our exchanger calculation. So if I go back to problem definition and application options, you see this is switched from the design with varying airflow where we started. We produced our optimum design, switched it into a rating case that would be ready to simulate in Hysys should we want to do that. You can verify what's actually happened. If I go into some of the summary of the geometry, there's a lot of detail here, but just looking at the summary, you'll see that the results of our design optimization, which were things like the number of bays per unit, number of bundles per bay, number of fans per bay, tube length, number of tubes, etc. These values now appear in black as though they were user-specified values in air-cooled. And when we run the rating case, we will be evaluating how this exchanger performs with the geometry that's been specified. With this rating case, you might want to save it as a distinct and separate file name. So let's do save as AC 101, and let's call it check. So let's summarize what we've achieved. We wanted to design an overhead condenser for a crude distillation process. We saw how we could import process and property data from Hysys into Aspen air-cooled exchanger. We used air-cooled's powerful optimization to optimize the design. In our case, it was for capital cost. We saw how we could review the design outputs, including setting plans and specification sheets. We saved our case and we prepared another case for subsequent simulation in Hysys at some point in the future. I hope you've enjoyed this demonstration. Thank you and goodbye.